Okay, so I give you three circles, any three circles in the world, and we start to look at their common chords. So let's name them omega 1, omega 2, omega 3, the names of the circle. Now the common chord between omega 1 and omega 2 is this one, and the common chord between omega 3 and omega 1 is this one. Now when we see the common chord between omega 3 and omega 2, let's draw it. I want you to prove that these three are concurrent, so to speak, they pass from the same point. It actually seems that they will when we draw the figure, and it's come out pretty neatly and nicely over here, but we want to try and find the reason behind it, why it happens, and then we'll explore that today. Let's see another one. I give you two circles now. And we look at their common tangent, the line which just touches both of them. Okay, this is an okay approximation, and then we draw the common chord. Yeah, so let's call this A, B, and let's call this C and D. When we extend this common chord, let this be X. I want you to prove that AX is equal to XB. Can we do that? Yes, we can, and we'll see how to do that today. And it's a pretty interesting result to think how the tangents and the common chords are related. Neat. Okay, so first let's learn some new stuff then today. So there's this concept called power of a point with circles. So suppose you have a circle and you have a point P inside it, or outside it even. Now you draw any line passing through P and you have a center O. Let this intersect at A and B. By definition, the power of point P with respect to this circle of center O and radius R is let's power of P is PO square minus R square. This is how we define it, the power of a point. But the really interesting thing we're able to do with it is that if we draw another line here, basically we have any n number of lines passing through P and intersecting the circle at two different points, we can say that PC into PD is equal to PA into PB. Pretty neat, right? Like we have a straight line and this point is dividing it in some ratio, and this point is dividing this in some ratio too. And what we're basically saying is, whatever lines you pass, suppose one side starts increasing, the other side will automatically start decreasing in such a factor that this thing remains constant. And what will it remain constant to is this number PO square minus R square, and we're going to prove that. Here's how it will happen. So we'll do it in this figure. So let's take a different figure. So we have this circle and we have P here, we have A, B, and we have the center O. Let's drop a perpendicular and let's call this X, this Y, let's call this Z. We know that this is R and this is R. Okay, so we're exploring PA into PB, right? Like in this line, like we talked about in the previous thing. So let's see what P into PB is. Let's see what PA is. Let's call this D. PA is AD plus DP, which is X, right? Now we know that since this is a perpendicular from the center towards a chord, that D is the perpendicular bisector of AB, right? So let's call this Z. And since DB is Z2, this part will be Z minus X, if that's relevant to us. So let's see what we can do here. PA is Z plus X and PB here is Z minus X. So what is this equal to? Z square minus X square, right? Now let's see what Z square minus X square is equal to in terms of maybe what we know when we have a circle. We know OP and we know R. In the previous page we discussed OP square minus R square. So let's see, in this triangle we have X square plus Y square equal to Z square and in this triangle we have Z square plus Y square equal to R square. So what should we do here then? Okay, I think yeah, we've got this right. So let's subtract these two. So we'll have X square minus Z square equal to Z square minus R square. And what else can we get? Not much, I guess. So let's see what we get from here. We wanted Z square minus X square, right? So we'll just multiply both sides by minus 1. So Z square minus X square equal to R square minus Z square. So we have Z square minus X square is equal to R square minus Z square. Now what is R square? R is basically the radius of the circle, and what is Z? Z is OP. So this is R square minus OP square. So in this case we have Z square minus X square is equal to R square minus OP square. Now the thing you'll see is the, okay, I think you can't see this, so we'll continue this here or here. So we have Z square minus X square equal to R square minus OP square. Now in the previous page we defined the power to actually be OP square minus R square. Now let's consider this. For any circle, I mean, you have O, you have P. You can see that if P is inside the circle, OP square minus R square will be negative since R is bigger. But if P is outside the circle and you do OP square minus R square, P is positive. So this is basically convention. So what we've got is PA into PB. In magnitude, it is always equal to OP square minus R square, which we've just proven since the magnitude of these two things are equal. So now we know that the power of a point which we defined as OP square minus R square is also equal to, for like any line passing through P intersecting at A and B, PA into PB. Now with this we have basically proven this for all possible lines. We can just change the configuration of PA into PB, but we can also like prove it with a very nice other way. So suppose we have P here and we have P A, B, C and D. So let's join these. So we know by vertically opposite angles that if this is X, this is X2, and if this is Y, then this is Y. So we know, and this is 180 minus X plus Y, and this is also 180 minus X plus Y. So we know that these two triangles are similar by the A rule. So let's try to write down the similarity. We'll go this way, X to Y. So we have PCB similar to X to Y, PAD PCB similar to PAD. And from this, let's try to form some relations. We have PC upon PA equal to PB upon PD, which implies that PC into PD is equal to PA into PB. So what this basically says that for any circle in this world, any circle, okay, any circle, if you have some lines passing through it, for any given circle and any two lines, this into this is equal to this into this. That's a really nice result, so to speak. And even more interesting thing is its converse. That for any two given line okay, not even line segments, let's just consider any 4 points. If you join them, their point of intersection, if from here you can generate this into this is this into this, you have just proven that these points are concyclic, and the proof of this lies in our earlier derivation, which I implore you to try to find out. Okay, now coming back to our problem. So what we've established till now, let's just go over what we've established till now. What we've established is that the power of a point, and P can be inside or outside, and this would still hold true, so to speak, that if this was a circle and P was here and we had this thing, still PA into PB would be equal to PC into PD. Notice how we're considering the whole length, not this thing. And this would also be equal to OP square minus R square. Right? And even more interesting case would be when we have tangents. Like suppose we have this A, B, Q, P. What happens in a tangent case is that if we actually magnify it, suppose we start off with two really close points and we have P here, so we have P touching these two. But when we, and in this case we would have, suppose they are C and D, PC into PD, right? Or actually it would be like this, we would have a line PC into PD. But when they're getting infinitely close, PC into PD is almost the same as PC square, and that is what is the case here. Here PA into PB will be PQ squared. Even more interesting. Okay, now let's try to use what we've learned today in this problem, our original problem. So how but we have to still see how are common chords related to that thing, right? Okay, so let's consider that first. So we have two circles now. It so happens that, let's say O1, O2, that for given two circles, if we consider the set of points, the set of points which have equal power with respect to both, it comes out to be actually this line. You can prove, and I'll give you a hint on how to, that all points on this line have equal power with respect to both the circles, which is a pretty neat thing, right? And here's how. And even if the circles are non-intersecting, you'll have this line. Basically this is called the radical axis of these two circles, and by definition it's the line which has the points which are equal powered with respect to both the circles. So we'll just try to prove or find where this is. So we'll assume that we have the origin here, so we have 0, 0 and 0, a centers, and let's say we have a point x, y here. So the power of this with respect to this circle, let's assume the radius to be r1 and r2. So power with respect to this is OP, which is this distance, point P, OP square, which is basically x square plus y square minus r1 square, and we're saying that the power is equal to this. Currently we don't know that this is a line, we've just taken a random point, and we're doing the power with respect to this one would be I guess x minus a square plus y square minus r2 square. So this is OP square. OP is this thing and radius. So once we open this, we have x square plus y square minus r1 square equal to x square minus 2xa plus a square plus y square minus r2 square. So we have this cancel out, this cancels out, and we have this. So we can just change the side of the things, and we have x equal to r1 square plus a square minus r2 square upon 2a, which is what? Which is a linear relation. So this tells you that this thing, the path of that point is a straight line, and since we have no x equal to c, the lines of the form x equal to c are straight vertical lines, just like with this. And suppose now you could argue that we've taken a special case, so we could move the circles around and we would shift the origin to that place and apply the appropriate rotations if required. So if you do this calculation in the case where the circles are intersecting, it turns out to be the line which is the common chord. You have to find out these coordinates too and see that they satisfy that line, which is homework for you because it's too much calculation for me. Now let's solve our original problems using what we've learned today. We'll solve this one first, which the problem was that we have two circles and we have their common chord CD and we have their common tangent AB. So we want to prove that if we extend CD and wherever it cuts AB, that point bisects AB. So we have some kind of relation between the common chord and the common tangent of two circles. So how do we do that? So first we'll try to write the power of x with respect to this circle, the bigger one. So let's see, since this is a tangent and x intersects here at 2 points, so we know that the power is equal to xd into xc, and it is also equal to xa square, which we did in the tangent case. And if we take the smaller circle, we have x intersecting at d and c, so we have xd into xc is equal to this xb square. So just a simple case, we equate these two and we have xa square equal to xb square and xa equal to xb. To think of it, that's how simple a proof can be when you know the right tools, right? Such a complicated relation or such a beautiful relation we have, and such a trivial proof, but it's good, you learn something. Okay, now let's consider the other one. Initial problem, I've just changed the figure, it's more neat this way. So here's how we'll go about it, is we'll assume that MN and CD intersect at P, and then we'll prove that AB has to pass through P. Now MN and CD intersect at P. Now since P lies on MN and MN is the common chord of 1 and 3, the power of P with respect to 1 and 3 has to be equal. So power of P with respect to 1 is power of P with respect to 3. Why? Because P lies on Mn and Mn is their common chord, which is also the radical axis, which is by definition the line on which all points have equal powers with respect to both the circles. Now we have P lying on the common chord of 3 and 2, circles 3 and 2, therefore P has equal powers with respect to 3 and 2, the common chord is CD. Therefore power of P with respect to 2 is power of P with respect to 3, since it lies on CD, right? So from here we can basically see that power of P with respect to 1 is power of P with respect to 2, just equal from this relation. And what does this tell us? If P's power with respect to 1 is equal to P's power with respect to 2, P has to lie on the radical axis. And what is the radical axis of 1 and 2? It is their common chord. Therefore their common chord has to pass through P. And we know it also has to pass through A and B, since that is the common chord by definition. Therefore AB, CD and MN are concurrent. Simple as that. And you're seeing how this technique is making proofs of such seemingly complicated things so trivial. Like we've basically proved this in 3 lines, which is really awesome. Thank you.